So let's do this problem. Here, this is section 1 and task 4. Here we have to prove that this equation is divisible by 9 with math induction. So in the first place, we check the base case, which is n equal to 1. And if we put 1 here, we have 1 plus 8 plus 27, so 36. It is divisible by 9. Next, we take n as a k, and if we put k here, we can already see that this is also divisible by 9. And in the next one, we take n as a k plus 1. So we have to prove that this is true for the next numbers. So if we put k plus 1 here, we have k plus 1 cube, k plus 2 cube, and k plus 3 cube. And here we open the brackets, and we have this thing, and we can say that see that k plus 1 cube, k plus 2 cube, and k cube is already divisible by 9 from the step 2. And here we have 27k plus 9k squared and plus 27, and we can take 9 out of the brackets, so we can also say that this is divisible by 9. So for k plus 1 is true. And in the next one, we have to prove that 5 to the power of 2n minus 2 to the power of 5n is divisible by 7. Here we also start from the base case, so n is equal to 1. And if we put 1 here, we have 2 squared minus 2 to the power of 5. And we have minus 7, which is divisible by 7. And in the next one, we take n as a k, and here it is also divisible by 7. And the next in the next step, we check for the next numbers, k plus 1. If we put k plus 1 here, we have this, that is equal to 5 to the power 2k multiplied by 5 squared, and the same with the 2. So and we take this to the modulo 7, and we know that 25 modulo 7 is 4, so 25 divided by 7, we have remainder 4, and for the 32 we also have remainder 4. And so we write this as 4 modulo 7, and if we take the 4 out of the brackets, we have this equation. And here from the second step, we know that this is divisible by 7 with 0 remainder, and so that's why 4 multiplied by 0 gives us 0 modulo 7. So this is divisible by 7. So in the next one, we have to prove this equality with using math induction. And in the first one, we have to check the base case, n equal to 1. And if we put 1 here, we can say that 6 equal to 6. So this is true. And in the next one, we take as n as k. And if we put k here, it is also equal. And in the third one, we have to check for the next number for k plus 1. And here, we already know that for the n or for the k, it is equal to this one, so we write this. And for the k plus 1, we just have to plus the k plus 1 multiplied to the next two numbers, and we have to check that this is equal to the to this one. It's this formula, but for the k plus 1. And if we take this multiplication out of the brackets, so k plus 1, k plus 2, and k plus 3, we have k over 4 plus 1, and here we do the same. So we take this out of brackets, and we have k plus 4 divided by 4, and we can see that these are all already equal, and in these brackets they are also equal, so they're the same. So we prove that this equality is true for the next numbers also. And the next one is similar to the previous one, so we have to also prove that these two are equal to each other. So first, as always, we check the base case. If you put 1 here, it is true, so 1 over 2 equal to 1 over 2 from the both sides. And the next one, in as a k, it is also true. And in the third step, we have to check this for the k plus 1. So this is here from here, so it is for k, and we plus this one, this is for the k plus 1, and we have to prove that this is equal to this one. It is also taken from this one, so we put here just k plus 1 instead of n, and we have to prove that they're equal. So we write this together, we write them together, so we multiply here k plus 2 from this, and we have this square equation. square. And we can see that this is this can be written as k plus 1 square, and also we can simplify the square with this one, and we have only k plus 1 here. K plus 1 over k plus 2 is the same as this one, so this is also true. In the last one, we have to prove this inequality. So 2 to the power of n is equal to or more than 1 over 8 for all n equal to or more than minus 3. In the first one, we check base case, but here it is not 1, it is equal to minus 3 from this one. So if we put minus 3, we have that 1 over 8 is equal to 1 over 8. So it is true. For the n equal to k, it is also true. And in the next step, for k plus 1, if you put k plus 1 here, so this can be written as 2 to the power of k multiplied by 2. And we know that 2k is more than or equal to 1 over 8. So we write this here, and since it is multiplied by 2, we also write this 2 here. And we know that 2 multiplied by the 1 over 8 gives us 1 over 4. And we also know that 1 over 4 is more than 1 over 8. So the inequality holds true here.
So this is section 2, number 5. In this exercise, we should define the sequence by I1 or A1 equal to 0 and A2 1 over 2. And actually we should find the first 7 terms of this sequence and prove that n equal to 1 over 3, 1 minus 1 over 2 when n minus 1. So first of all, we just use this formula to find R3, R4, R5, R6, and R7. So R3 is equal to 1 over 4, R4 it's 3 over 8, R5 it's a 5 over 16, R6 it's 11 over 32, R7 it's like 21 over 64, and so we found the 7 first 7 elements, and then we should prove this formula. So we use mass induction for this. So we just imagine that n equal to k, and then our formula will be with k equal to this one. So then we should use n equal to k plus 1, and then k plus 1 will be this formula. We just use it. Okay, and then we use this formula from the beginning, like this one, and then we just replace rk with this formula and rk plus 1 with this formula, and in the end we just then simplify it and got this one. It's like the similar with this formula. So yes, the next one, it's 12 exercise. So in this exercise we have a b c d, okay, and the rise is given Rn. It's equal to 3 multiplied by Rn minus 1 and minus 2 multiplied by Rn minus 2. So the rise is also given R0. It's like a 2, R1 equal to 3. So in A, we should find the first 5 terms of this sequence. So of course we use this formula to find all of 5 terms, but the rise is given the R0 and R1, so we start with R2. R2 equal to 5, R3 equal to 9, and R4 equal to 17. So in the B, we should guess formula. So guess formula I use in the first 5 elements, and so in here we can see some formula between them. It's like Rn equal to 2 in the power of n plus 1. So R0, for example, equal to 2 in power of 0 plus 1 is equal to 2. So it's like the similar with the sequence. And for example, we also take R3, it's like a 2 in power of 3 plus 1 equal to 9. So our third element, like 0, 1, 2, 3, our third element is also 9. So yes, we suggest that this formula it's really relevant for this sequence. So in the C, we should verify that this formula is correct. So to verify it, we use mass induction. So we imagine that n equal to k, k equal to n in power of k plus 1. And then we suggest that n equal to k plus 1 and k plus 1 equal to 3 multiplying by ik minus 2 multiplying by k minus 1. So I guess yes. Also, forgot about this. How can you see in this formula we have k minus 1? So to find k minus 1, we just use it n equal to k minus 1 and find this formula. So in the end, we just replace ik with this one and ik minus 1 with this one, and then we just simplify it. And in the end, we have 2 in power of k plus 1 plus 1. So yes, our formula, this formula is suitable for this sequence. So formula in the D, we should find formula for n that involves only one preceding terms. So we use n equal to 2 in power of n plus 1, and n minus 1 is equal to 2 in power of n minus 1 plus 1. So then we just use this formula and we simplify it, and in the end we get this one. So let's move on to section 3. In this section, we do exercise 4. So in this exercise, we should solve the recursion relation where n plus 1 equal to 7, n minus 10, n minus 1. So there is given also r1, which equal to 10, and r2, which equal to 29. So we use formula from the slides, and we just take 7 here and minus 10 here, and then we just solve this equation. We have found dominant and r1, r2, which are 2 and 5 respectively, and then we just take this formula, n equal to a multiplying by n in power of n plus b multiplying by p in power of n. So we use these two terms to define a and b. So when r1 it's equal to 10, we just take it and solve. With help using this equation, we can find that a equal to 5 minus 5 over 2 multiplied by b, and by using r2 we can find that r2 equal to this equation, and we just replace a by this formula, and then we can find b, and of course by using b we can find a. It's 7 over 2, b 3 over 5, and then we just take it on this formula, and this is our final answer. So in the 6th one, we should solve the recurrence relation. It's like very easy to solve. We use formula, we put 5, we put 6, and then just solve it by using the dominant. So r1 it's like a minus 6, r2 1, so we just use formula, and our final answer will be n equal to multiplying by minus 6 in power of n plus b. So that's all. Thank you for your attention.
In review chapter 5, number 5, we need to prove that this case is divisible by 3 for all n in range of greater or equal to 1. At first, we need to check the base case. Base case is n equal to 1 by the condition. We substitute 1 to the equation, then we get 1011. Which code is this divisible by 3? Yes, it is, so we can make the step number 2. Step number 2 is the finding inductive step for next elements. So we replace n by k plus 1 in the base case. So we get 10 in power of k plus 3 plus 10 in power of k plus 1 and plus 1. If we simplify this, it will look like 10 multiplied by the sum of 10 in k in power of k plus 2 and 10 in power of k plus 1. So in the third, we need to find the induction for some integers of m. We make 3 multiply m because we need to find is this divisible by 3. We substitute 3m like equality of the base case in condition, so we replace 1 from the left to the right, so we get 10 in power of k plus 2 plus 10 in power of k is equal to 3 multiply m minus 1. We substitute this into inductive step for the next element, So we get 10 multiply 3 multiply m minus 1 plus 1. So we get 30 multiply m minus 9. If we simplify this, we get 3 multiplied by the difference of 10 multiply m and 3. Because of 3, we can see that it's divisible by 3. So answer is it's proved. In number 10, A and B, we need to find the formula of an element. So as we can see the condition, we have one in each bracket. We can represent it like equality of the second element. So we get that last element is look like n minus 1 divided by n. As we can see, the numerators of next element is divisible to the denominators of previous by 1. Like 2 divisible by 2 is 1, 1. So we can say that the formula of an element is 1 divisible by n. We check out it by substitute 4 and 5. So we get these answers, yes. In number B, we do the same. We represent one in each bracket, like the equality of the second element. So we get the last element is n in square minus 1 divisible by n in square. We use the formula of abbreviated multiplication to represent n square minus 1, like n minus 1 multiplied by n plus 1. So we substitute this into the formula using the second element, the third, fourth, and etc. So the multipliers of numerators, all numerator is n minus 1 factorial, and the second element, second numerator, multiplier of numerator is n plus 1 factorial divided by 2. So all denominators can be represented by n factorial in square. So we make the final formula. It's n minus 1 factorial multiplied by n plus 1 factorial divided by 2 multiply n factorial in square. So we can represent n minus 1 factorial like n factorial divided by n. N plus 1 factorial we can represent like n plus 1 multiplied by n factorial. We divide it and like simplify the formula. So we get n plus 1 divisible by 2 multiply n. In number 12, we need to find the sum of elements. This is the given condition. Like we see in the given condition, the first element is 529. The difference of each element is minus 4, and the last element is minus 459. We use the formula of an element to find the value of all elements, the n. We substitute values in given condition to this formula, so we get minus 459 equal to 529 minus 4 multiplied by difference n and 1. So we replace 529 from the right to the left. We get minus 988 equals to minus 4 multiplied by difference of n and 1. So we divide two parts of equation by minus 4, so we get n minus 1 equals to 247. We replace minus 1 from the left to the right, so we get the number of elements is 248. Third, we use formula of sum of all elements. We need the value of elements, the first element and the last element. We substitute all these values into this formula. So we get that sum of 248 elements is 4680. That's the answers.
So today we have 3 exercises from the review parts from the chapter 5, and the first one is the 15th exercise. It's pretty simple arithmetic sequences, and in the A part we have to find 30 seconds and 100 terms in this sequence, and the first term is 5, second is 3, and the third is 13. And we then understand that if we subtract 9 from 5, the second from the first, the common difference is 4. So if we apply this to the formula that is given, we can understand that a 30-second term will be 129, and 100, so it will be 401. So I'm sorry, there's a little mistake. I mean, right here, 4 multiplying 100 and plus 1 will be 401, not a 400. And why this answer is right? Because if the answer, the final solution, gives us a whole integer, a whole number, so this is a right answer. And the second one, let me just, does 125 belong to the sequence? If so, where does it occur? So just a second. So we got that the common difference 4, and if we apply the same formula, so this like 4n plus 1 is 125. So if we subtract 1 from 125, it will be 124, and if we divide 124 from 4 to 4, the answer will be 31, a whole number in an integer, so the answer is yes. So the C right here, we have to repeat B for the numbers 429 and 1000. So for 229 we apply the same thing, and as you can see, if we divide 428 to 4, the answer is 107, which is the right answer. But if we do the same thing, like dividing 999 to 4, the answer will be wrong because it's not a whole number. There's like 249.75, which is not the right. So the last one, finding the sum of the first 18 terms. So as you can see, there is a formula for understanding it. So we have 18 terms, 18 terms dividing by 2, in the brackets 2 multiplying to 5 plus 17 multiplying to 4. So I guess you can see the answer is 702. So the next exercise on the list is 1, 2, 3, and we have to solve the recurrence relation. Like, I guess, at least, I mean, I hope you can understand. I have a hard time to pronouncing all these given thing. So let's get into the solution straight away, like this. So assume that an equals to r in nth power, and there is this formula. I guess, I hope you can see it. We divide it by r n minus 2th power. We have r2 minus 5n plus 4. So if we do it in the brackets, simplifying, r equals to 1 and the second equals to 4. So, and by this formula and applying it to general solutions like this, so we can understand that 3b equals to 9. So if we divide 9 by 3, b equals to 3, and the final answer is right here. So let's get into the last exercise. Is 29. So in this last exercise we have to like let an be the sequence defined by a0 in the base equal to minus 2, a1 minus 2, and an equals to minus 6an minus 1 in the base minus 9an minus 2 in the base for n more or equals to 2. So find the first 5 terms of the sequence. Solution. I guess you can say that the first solution is 1, the second is going like this, is equal to 12, the third one equals to minus 81, the fourth term is 378, and the last is minus 1539. The final answer, the first 5 terms is minus 2, 1, 12, minus 81, and 378. If we apply to the given formula. So B, find the formula for an. Solution. Okay, we have to find the characteristic equation. So the recurrence relation is linear and homogeneous. Assume that an in the base equals to our n and nth power. So our nth power equals to minus 6r n minus 1 in the power minus 9r n minus 2 in the power. So we divide it by r n minus 2 in the power of stepeny. So I guess you can see it right here, and it's equal. It will be like r squared plus 6r plus 9 equals to 0. So it will be also double root if I guess you can see that r plus 3 in the brackets ns squared equals to 0. So r equals to minus 3 will be double root. So if we apply this result to the given formula right here, and we substitute, a equals to minus 2, the final answer will be like an in the base equals to, in the brackets, minus 2 plus 5 over 3n multiplied just multiplied to minus 3 in the nth power. So that's it for the 3 exercises. I hope it was pretty understandable. If you have any questions, you can ask us directly.